Today we will discuss the last topic of the chapter, the unit I would say, that is applications of determinants and matrices. In the beginning of the unit only we had discussed this application of determinants and matrices. Today we will see how it is applied. So we have taken a system of linear equations. You can see I have written three system of linear equations in three variables x, y and z. This is heterogeneous system of linear equations. We can have homogeneous system of linear equations also. In case whatever number of linear equations you have got in the system, if at least one of the constant or at least one of the equation has got non-zero constant, then it is heterogeneous system of linear equations. In case every equation has got constant equal to 0, then it becomes a homogeneous system of linear equations. So assuming this is a heterogeneous system of linear equations, then you can see it consists of constants, variables and the coefficients of the variables. I have assumed A to be the matrix of coefficients, capital X is denoting the matrix of variables and B is denoting the matrix of constants. Now if these be the notations used for the terms related to the equations, then you will see that the system of linear equations can be written as product of these two matrices, which will result into the matrix B. You can verify this by simplifying the way the matrices are being written using matrix multiplication. So matrix of coefficients multiplied with the matrix of variables, and on the right side I have written matrix of constants. We can quickly check whether this gives rise to the system of linear equations or not. You can see this matrix is of order 3 cross 3 and this one is of order 3 cross 1. So we know the product is possible because number of columns of first matrix and number of rows of second matrix are equal. Moreover, the resulting matrix will be of order 3 cross 1. You can see the matrix on the right hand side, it is of order 3 cross 1. So let us quickly check. On taking matrix multiplication, are we going to get this or not? Okay, if we conduct the multiplication, you will see for the first element, these first two elements will multiply with corresponding elements of the column and the products will be added. So we get a1x plus b1y plus c1z. So the first element comes out to be a1x plus b1y plus c1z. Because we don't have more columns here, so just one element in that row. So moving on to the next one, a2x plus b2y plus c2z. So second row will also have only one element that will be equal to this. Then a3x plus b3y plus c3z. That is the left hand side of the third linear equation. So what are we getting? On the left hand side we are getting a matrix which will have first element as this in the column, second element will be this, third will be this. So on the left we are going to get a matrix of order 3 cross 1. On the right also there is a matrix of 3 cross 1 and they both are equal. And when two matrices are equal, that means their corresponding elements are also equal. So the first element of product of this matrix will be equal to D1. So we saw when we go through the multiplication, the first element comes out to be A1x, then plus B1y plus C1z. It will be equal to D1. So we can certainly say that the system of linear equations given to us can be written in this form. Okay. So if I take the system of linear equation in terms of notations as Ax is equal to B, and assuming A is non-singular, that means its determinant is not equal to 0. We have discussed if determinant of a matrix is not 0 square matrix, then we can talk about its inverse. So if the determinant is not equal to 0, we can assume the inverse exists. Obviously it will exist. We can multiply both the sides by A inverse. Then here A inverse into A reduces to I. A inverse into B, because we don't know the matrices, matrix A inverse, so we cannot multiply, so I'll keep it as it is. Now identity matrix into X will be the matrix X only, because any matrix if it multiplies with the identity matrix, we get the matrix itself. So X is coming out to be A inverse B, and we know how to evaluate A inverse. It is adjoint of A divided by determinant of A. So X, which is denoting the matrix of variables which we are interested in knowing, will be equal to what? 1 over determinant of A multiplied with the product of adjoint of A into B. So what we have to do? We will first quickly check what is determinant of A. Firstly, it should not be equal to 0. Then only we will proceed. If it is not equal to 0, you find adjoint of A by evaluating all the cofactors. So this is a matrix of transpose of cofactors, and matrix B will be known to us. Multiply both the matrices. Then each element of the matrix will get divided by determinant of A. That will give us the matrix X, or you can say the values of variables X, Y and Z. Okay. So this is how this provides us the unique solution for the system of linear equations. Therefore, we call this system as consistent because it is providing us with the solution. Now let us quickly discuss another condition. If determinant of A comes out to be 0, then there are two possibilities. Either it will be inconsistent, the system will be inconsistent, that means they have no solution, or the system may be consistent but with infinite solutions. That will depend upon this product. So if determinant of A is 0, we need to check what is this product. What type of matrix is this product? If the product of adjoint of A dot B multiplied with B does not comes out to be a null matrix, this is not 0, this is null matrix. That means, null matrix means all the elements of the matrix are 0. So if it happens, this product is not reducing to a null matrix, then the system will have no solution and the system will be termed as inconsistent. If this product comes out to be a null set, that means all the elements of adjoint of A into B are 0, then the system will be consistent because it will give us solution, but the number of solutions will be infinite.